Hi, welcome everyone. This tutorial will show you how to make a traditional Snake game in Niantic Studio. The concept of the game came from a traditional Snake Tetris game which I played as a kid. We will recreate this game today in Niantic Studio using Gaussian splatting scan made with Scaniverse as a game environment. Here are the things we're gonna learn in this tutorial. We will learn how to code game mechanics for a Snake game. We will learn how to use input system to control Snake on desktop and mobile. We will learn how to implement top-down type of camera to make camera follow the Snake. And we will make a force field asset using custom shader material and many other things. So let's get started. First of all, let's create a new project. For that, you can go to Niantic Studio workspace and press new project. Let's call it Snake Game. Let's press create button. So let's pick empty project because we're gonna create everything from scratch. For this tutorial, you will need to go to GitHub, where I posted all the assets you need and all the code parts you need for making this project. Now, as you can see, we have a new project created. All we have here is a camera, which will show our scene. We have directional and ambient light, which is default lighting setup, and we have a little box here, like as a test asset. First thing we're gonna do is we're gonna drop all the assets necessary for our game. And for that, you can go to GitHub and download these three assets: force field GLB, snakehead GLB, and temple SPZ. So let's grab all our files we got from GitHub and drop them to Niantic Studio. First, we're gonna import our environmental scan, which will be our asset for the level in the game. And I'm gonna use this temple SPZ file, which is a scan of a street where I've been working on this project. I made the scan using Scaniverse. Scaniverse is an app made by Niantic, and you can use your phone to scan an environment to create an asset, like a Gaussian splatting asset, which I did for creating this environmental scan for the game. So let's do that. Let's drop this temple SPZ into our scene. And as you can see, now we have this street asset in our scene. Let's now position and rotate this asset in order to make it a level where the snake can travel in the game. We can use this road in the street as our play area, and we positioned the asset the way that this box is standing on top of it. So our snake in the future will travel here in this play area. And as you can see, there is an axis here which shows our directions of the where the X, Y, and Z axes go. So the snake will travel across X and Z axis. In this positioning, we can use the environmental scan as a level asset. Let's now try to use this box to measure the playable area. The playable area will be the area where snake can travel. So we can just rotate the box and rescale it to see how big the area is. As you can see, we rescaled this box to define a playable area. So we have now this box showing where the snake will travel in the level. In the future, we will replace this playable area with a force field. Right now, it's just a box, like a utility box, which helps us to see and measure the playable area. So let's write some code. We're gonna implement the main logic for the snake. First of all, we need to define the rules of the game. And the rules for these games are very simple. Player controls the snake to collect apples. Apples spawn with random positions at the start. If the snake collects all apples, player wins. If snake hits the wall of the level, player loses. Or if snake hits its own body, player loses. Every time snake eats an apple, the snake length and the speed increases. So what do we need to implement this game logic? We need a system for managing apples. We need a system for managing snake segments, or in other words, snake parts. We need collision functions for the snake, and we need a game state. So let's implement these code parts to create a basic game logic for the snake game. First of all, let's create an empty object and call it snake. Then let's create a snake script. So we go to files, new component file called snake. And Niantic Studio has code editor inside, which we're gonna use. And I already prepared the code which you can use for the start. So we can go to the GitHub, and we can go to code parts. We can go to snake start TS, and we can just copy paste this code into our code editor window. That's going to be our initial code, which implements the systems we mentioned, the system for managing apples, snake parts, collision functions, and game states. We will need an extra file, like a library for serialization, which I will mention later. Let's create a new file, serializer. And for serializer, you could go to the GitHub and grab it from final code, serializer TS. Okay, let's hide now the box, because we needed it only for measuring the playable area size. Now what we have to do, we can go to the snake object and add snake component. Snake component will be our game logic. So let's press build or press Ctrl S to build an app. Now the app is built, so we can press play to run a simulator and see the result of our first code. And as you can see, we can have here the apples, they spawned in random positions, and the snake goes upwards and it collided with a wall, the boundary of the play area, and it stopped. So that's the very basic game logic. Let's go now through the code, and I will explain how different code parts work and what are they responsible for. So we can go to the snake TS, which stands for TypeScript. Here we import all the necessary libraries. We import ECS, which is a standard library for entity component system from Niantic. We can have our serializer, which is a library which helps to save special data types in our component. And then we're using 3, which is 3GS library, which is Niantic Studio utilizes. So the first part is the apple's logic. Basically, this function responsible for spawn apple. It receives the boundary, the grid size, the world. The grid size is the basically grid step in which our game operates. It's how our snakes moves. It moves through steps, and our apples will be spawned in this grid, and the grid is defined by the grid size. The world is a property we're gonna address to set positions of different entities in Niantic Studio, and the boundary is our boundaries of the playing area, which we measured earlier. The next function is apple collision. Edges basically says if position of the head snake and apple position, the distance between these are less than the grid size, then it means that we collected an apple. So this function responsible for collecting apples. And next one is a check boundary collision, is a function responsible for checking whether we reach the boundary, if we hit the wall of the playing area. And this is very simple logic. Basically, we just drop head position and the boundary, and it checks. It returns if we're outside of the boundary. The next one is a check self collision, which is basically a function which checks if snake collided with its own body. It goes through all the snake parts and basically says if some of the snake parts have the same position, then that means we collided with its own body. Then we have some of the code parts here to implement, which I will cover later in this tutorial. UI logic, which we're gonna show the messages of the main events in the game. Reset game logic, if the game stops, if we win or lose, then we need to reset the game. The input system shows how we can actually interact with the game using touch events on mobile and keys on keyboard. This I will skip for now. Reset game, and I go to the main game component. Main game component is basically the main component we're using to implement game logic, and we're using a component system of Niantic Studio. Here's the list of data parameters we need to make this game. We have segment positions, is the positions of the snake segments. Then we have segment entity IDs, is an array of snake part entity IDs. Then we have the same for apples. We have apple positions, is an array of apple positions. Then there is an array of apple entity IDs. Then we have amount of apples to spawn. We have direction of the snake. We have time step, a duration of one step the snake goes. So basically, if it's, let's say, 1 second, then snake will move every 1 second. A speed multiplicator, after each apple picked up, the snake will go faster. So the speed of the snake will be multiplied by this multiplier. Then the time of the last move. At the time of the last move, we need basically to make a sequential movement of the snake, because snake will only move each second, let's say. Grid size defines the grid where we spawn apples and where the snake moves. Boundaries is the play area boundaries, and game over state. Game over state is when the game is over, we will save this in this property. Then let's go through the functions. The first function is add. It's basically when we're adding component to the scene, and what it does is initiates all the properties. Tick, it's an update function which runs through the game, and that's where the game iterates. This is our main game loop, and this is main code parts for updating the game. And I can quickly go through it. If the game is over, we just not iterating here. And here is the part for sequential snake movement. Here we take all the parameters and deserializing them. What it means is we want to save certain parameters into the Snek component. And right now Niantic Studio has limited amount of data types, and we need actually to use more data types. For example, an array of positions or array of objects. And for that, we're using serializer, which basically take our custom data type and converts it to a string and saves string into component. And we could extract the data the same way. We're taking a string from the component and we're converting it back to the original data type. Serialization helps us to implement new data types and save them into the component. And we do it for Snek parts, for apple positions and apple IDs and Snek IDs and other data. For example, boundaries is an object, and we also can save it due to serialization. This part helps to move the snake. It just basically updates snake body to move one step forward. Here we're defining where the snake goes depending on the direction of the snake. Here we updating the head position. So we're taking head position of the snake, which is the first segment of the snake, and we moving it towards the step, and step defined by this snake direction. So this logic basically moves the snake. And here we're updating the entities of the snake position. So basically each snake segment is an entity in a scene, and we need to update the position. So let's say each part of the snake is a little sphere mesh, and to update its position in the scene that we can visually see that this little sphere moves, we need to set the position of this segment, and this line basically does it for us. Part we're checking collisions, we're checking snake self collision, we're checking boundary collision, and if snake hits itself or hits a boundary, the game is over. It says that the game is over. And the last part here in update is check for apple collision. So we're just going and checking if snake ate an apple, then we basically make snake go faster, and we remove the apple, and we create an extra entity, which is the extra snake part. So we extend the snake, make snake go faster, and we remove the apple. And if snake eaten the last apple, which means the game is over also, and we won the game. And the last code part I want to go through is initialization of the game. And if you go to this method called add, it has this function called reset the game. Reset the game is a function which basically initializing all the properties of the component, and this function will be called on game initialization and also reset of the game. That's why we need this function outside of the main component. So if you can go and see here, it initializing all the main parameters, including boundary, and boundary size we took from our measurements we did earlier. And then we initializing the snake segments here and spawn the entities into a scene of each snake segment, the same we do with apples. And we have a function called cleanup. So cleanup basically deletes all the apple entities from the scene and all the snake segments from the scene. Okay, let's talk about input system. So we have now snake which moving through the scene, but we want to control it, and we want to control the snake on both platforms, on desktop and on mobile. How we do that? Let's start with the desktop. To control the snake on a desktop, we can reuse Niantic Studio Input Manager. So to control Input Manager, we can click somewhere in the scene and we can go to input manager, and we can create actions. Each action represents certain input action. So we need to create 4 different actions for each direction of the snake. We go and we create up, down, left, and right. So we have now 4 different types of inputs, and we need to add different bindings. So for example, in case of up, we can assign W key and we can assign arrow up key. We can go here and say W key, and we can go and say up. And we need to do the same for all 4 of them. So as you can see, I defined all 4 of them. There is down, left, right, and up. And we either can use WSAD or arrow keys on the keyboard to trigger input events. Now let's check how we can implement using this input manager into our code. Let's go to the Snek script again and add an input part here. So first of all, we can go to the full Snek code and find a function called detect platform. So here is detect platform function, which will help us to detect the platform. This function will help us to define whether we run an app on mobile or desktop. Let's go to GitHub and search for handle inputs part. So this is part which helps us to handle inputs on desktop and mobile. Let's copy it into our code. As you can see, we need to implement new property called last direction. We need last direction to track the last direction of the movement. And this logic helps us that the snake is not running into itself. Let's say we're going to the right and we press left right away. And to avoid snake going into itself, we need this logic. So every time, let's say we press up, we check that the last direction is not actually down. And if that's the case, we're assigning the new direction. So we're taking an input key, checking the last direction, and assigning a new direction. That's the logic for all the keyboard inputs. So we have 4 of them. And for mobile inputs here, as you can see, we're using a component called swiper. So basically, swiper is a custom component we're gonna implement a little bit later. And what it does input in a similar fashion. It's taking a direction from the swiper and implementing the same logic, defining the direction of the snake. Swiper is custom component we're gonna implement, and it's checking touch swipe direction. If we're using mobile and we swipe our finger through the screen, the swiper component will define in which direction we did a swipe. We need to add swiper here in our snake component. So to do that, we go up and adding here swiper, and we're adding also last direction into our component here. We also need to add a swiper into our schema. So let's do that. So basically this schema is the public properties of our component, and we want to use swiper as a external component, and we want to wire it up here to our main game logic. So we create a public property swiper, and we're gonna add swiper through the scene editor. Let's implement a swiper script. Let's go to new file, new component, call it swiper, and let's copy paste it from the GitHub. This swiper component is pretty simple. We basically creating a new component, and when we're adding a component, we creating event listeners. And these event listeners are on touch start, on touch move, and on touch end. And we're creating a logic which tracks the swipe direction. And then we save the touch direction into schema touch direction property. So if we now go into the scene and create an empty object and call it swiper, that will be our swiper component which tracks the swipe direction on mobile. Let's add swiper component to the object, and as you can see, this is a property which will show us the direction of the swipe. Let's go to Snek component now and assign the swiper into Snek component. So let's save now and rebuild the project and see if we can control the Snek with the keys. We can press Ctrl S or Command S on Mac. Let's run a simulation and see if we can control the Snek with the keys. As you can see, now I'm controlling Snek with the keys. I'm using WSAD, as well as I can use arrow keys. And if we run this game on mobile, then we can actually swipe our finger through the screen to define the Snek direction. Okay, let's now talk about UI. We have different events in our game. When we, for example, start the game, we want to show instructions how to play the game. Then we have events like when we're winning a game or when we're losing a game. We need to show this as a message as well. So let's introduce a UI system which is gonna display different messages in our game. To do that, we can go to create new object and let's add UI elements. Let's rename it to message. And let's define the properties. This is similar to CSS, how we can display this element on the screen. That's how we set it up. You can check all these different properties. Basically font size 24, we're using a pixel font to emphasize the idea of the game. Width of the text, margin top, and that we place our text field a little bit off the top, and then we put it in the center. We have a green color, we have background, slightly transparent, we align text to the left, and we write text test just to see where our text will show up. And we can press save, rebuild, and then we can run and simulate it and see where we will have our message UI elements. And as you can see, once simulation is running, we have this field which displays our text. Now we can implement code parts to display the main events in the game as UI messages. To do that, let's go to Snek script and add these code parts. First of all, let's grab this UI logic part from GitHub, Snek file. We can go to our Snek script and add it here. Then we can show main events through the code. Let's start with show navigation instructions at the start. Once we just run the game, we can show navigation instructions. We can grab this code from the GitHub as well. Let's put it here, show navigation instructions. And as you can see, with depending on the platform, we use arrow keys, or if it's mobile, we can write swipe direction to move. And we drop a time as a parameter to show message function. The idea behind that is when we show our message, it should disappear after a certain duration, and this UI logic implements that. We have a function for show message where we just define a text, and then once we run update message in our game loop and time of the message is more than message state duration, the message will disappear. Let's implement messages for events like winning the game and losing the game. We can also grab these from our GitHub. As you can see, I will take a message for game over when we self-collided, and game over when we hit the wall. And also we can show when apple is eaten, we can show a message. Then we can go and show a message when we win the game. And also we need to place a function called update message. This is important that our message disappears after a certain time. So we can go to tick of the main game logic and add here update message. This function will track the time, and after a message is shown a certain amount of time, it will hide it. And as you can see, we need to add message property to our schema. So basically we need to wire up message as public property of our main game component. So we can go here and add message. And once we go to Snek, you can see there's a new property called message, and we can add message here. So we basically have our message system, and we're connecting it to the main game logic. Let's recompile everything and see. So it compiled. Now we can run the simulator and see if we can display main events of the game as a message. As you can see, when we run a game, it shows us welcome, use arrow keys to move the snake. Once we, let's say, eat an apple, it shows us that apple is eaten, and once we, for example, hit the wall, it shows us game over, you hit the wall. So that was the part how we implemented a UI system to our game. And as the last thing, let's delete first message here, clean it, and let's move on to next part. So let's implement a reset game logic. Every time player wins a game or loses a game, we need to reset the game, that the game starts from the beginning. To do that, let's add a bunch of code to our Snek game component. We can go to GitHub and to the main game part and copy reset game logic. Then we can go to Snek in our project and find this part and replace it here. So this part, what it does, basically we have now a function called start game reset, and once this function is called, the reset of the game is started. It will show a message: the game restarts in 3, 2, 1, and game will restart. So we have a function called start game reset and a function handle game reset. Basically, these two functions will take care of the game reset. Let's add them into our main game loop. So if we can see the start game reset, we have in parts like when the game is over. Let's say we can scroll into a part where the snake collides with a wall, or a snake collides with itself. Then we need to restart the game. Or when we actually win the game, that also the time when we need to reset the game. So these are 3 parts to reset the game. And now we need also to handle a reset, which gonna show us countdown of the reset, and we'll do the actual reset. Handle game reset. Handle game reset. So reset game logic. This part is at the beginning of our game loop. We can add it here. And as you can see, if the game is over, then this part will handle the game reset, will show us a message of countdown, and it will do a cleanup. We'll remove all the apples and snake parts from the scene, and it will reset the game. Basically reinitialize all the parameters of the game. We need to add one more part to clean up. We want to actually remove the message as well as a part of a cleanup. And let's grab that code here from the final code. Remove the message. Send it here. Remove the message. It will just update our message system and we'll clean up the message. So that's how we implemented a reset function of the game. Let's see how it works now. So once we run a simulator, let's, for example, hit the wall and let's see what will happen. So game over, you hit the wall. And then we have this message which says game restarts in 3, 2, 1, and the game restarted and we have a new game now. So as you can see, the reset game function now works. Next step of this tutorial will show you how to create a force field. As you can see now, the problem of this game is that the boundaries of play area are invisible. The player right now doesn't know whether they're gonna hit the wall or not. So how are we gonna do that? How are we gonna implement a force field around the play area? Let's return to our box. This box we use to measure play area. And let's create a custom material which will show a force field around this box. I created a special mesh for the box to use it for a force field rendering. This box has 6 sides, but we actually don't need top and bottom sides of this box. So I created in 3D modeling software box with only 4 sides, as you can see, and I flipped the normals that the sides of the box, they facing inwards of the box. So let's use this new mesh called force field instead of our box. And the size of force field is exactly the size of the box. So we can use the same measurements we used for the box to resize the force field. Once we hide the box and leave only force field model, you can see that now we have a little fence around our playing area, but it looks like a gray wall. What we want to do is use a custom material to display it as a force field. For that, we can create a new component called force field. Let's grab the code of a force field in our GitHub. Let's put it here. Let's add a force field component to the force field object and recompile the project and run it in simulator. And as you can see, now we have a little force field around the perimeter of the playing area. This force field is animated and represents this gradient blue energy field. So let's go through the code of a force field really quick, and I will explain how to implement something like a force field. The concept here is very simple. We're taking a model of a fence and we're creating a custom material called shader material, and we add this shader material on top of the fence object. So if you can see, there is an add method where we're creating a shader material, then we're removing the original material from the object and we're replacing it with our shader material. I wrote an extra hack here because I realized that the model takes time to load, and sometimes we have extra sub meshes inside the model which require also that their material should be switched. So we're checking if the model is loaded, and if it's not, basically we're grabbing the entity, we're grabbing the force field object, we go through all its sub meshes, and if we find some material doesn't have a type of shader material, we applying our new material, and we're also setting rendering order 9000 that this material renders the last, that we can actually see it. And about this shader material, I will explain a little bit how it works. So basically we're setting up our shader material, we're creating a parameter time because our shader is animated, so we need to add time, and we're updating this time and a tick function. And here basically the shader consists of vertex shader and a fragment shader, and a vertex shader, it's a standard function. There is not much to say about this, and we're only saving the world position of our mesh into position variable. And in the fragment shader we're creating a gradient from bottom to top of our mesh. Then basically this code just creates a gradient, and then we're adding a little bit of animation which will animate the gradient in a sine wave type depending on time, and we're adding a blue color to it multiplied by the gradient. So, and the return function of a shader which defines the color of our material basically sets a blue color and the gradient, height gradient as a opacity. This is a pretty simple shader which basically creates animated gradients as a force field. If you want, for example, to change the color, you can change this variable to different one and you will have a different color. If you want to see more shader examples, you can check out this resource called Shader Toy, which is a good way to learn about shaders. Shadertoy.com. It has a lot of different examples of shaders. This is one of the oldest resources if you want to dive more into it and create more cool shaders for your projects. Next thing in our tutorial is snake head. So let's add a snake head as a textured mesh, which we will direct to the direction of the snake. It adds personality to the main character of the game and it just makes the game more engaging. I created this model called snake head, which you can grab and drag and drop into the main scene. As you can see it here. You can make it a bit smaller. We can use this variable 0.125. This is exactly the size of other snake segments. And let's add code which will now direct snake head into position of moving direction. Let's go to snake component code. First of all, when we create a snake, and cache our entity IDs for the first segment, instead of creating an entity, we will just grab a snake head, which we already have in the scene. And for that, we also have to add snake head as a public parameter. To our snake game component. So we now have snake head as a public parameter. If we go to snake in our scene, we can assign snake head. So now let's add a code which will rotate snake head to the direction of the movement. Let's go to our final code and find a piece of code for rotating snake head. All it does is basically taking our next step direction is a step snake makes a move towards, then we rotating ahead towards that step and setting world rotation of a snake head with that rotation. Let's recompile the project and see if it works. So as you can see now, when we using arrow keys, we have snake head in front of snake, and it changes rotation depending on the movement direction. Let's introduce top-down camera, a component which will help us to automate camera movement. The camera will follow the snake automatically. To create the camera, we can go to files and we can create a new file. Let's call it camera top down. We can go to GitHub and grab camera top down script, copy paste it to our window, and then we need to go to camera object and add our camera top-down script. Let's also define a target entity, which is our snake. What this script does is basically it creates a top-down type of camera which will follow the snake. Let's go through the script a little bit. It's pretty simple. We're defining a component, we're saying that's our target entity, following distance, following height, smoothing. And it's pretty straightforward. There is only tick function, which basically takes target position, which is a position of the snake, and it smoothens the position of the camera between current camera position and previous camera position. And the same happens with the rotation. We're getting a rotation from current camera towards target, and we're saving the previous camera position, and we're smoothing them a little bit with the slurp function, which is basically linear interpolation between current camera rotation and the previous camera rotation. And we're using smoothing coefficient 0.1. You can play around with it for different types of smoothing, but basically that's pretty much it. Let's save and rebuild our project and see how it works now. As we're running a simulator, we can see now camera smoothly follows the snake, which makes view more cinematic and interesting. And as the last part of this tutorial, let's publish this project to let other people play it. For that, we can press land, and that's where we can save our code. We can add snake game first, edit, and we can press land files. That will save our code into Niantic Studio repository, and let's publish our project. For that, let's press publish and pick our latest edits and press publish. You can edit a cover image and the name. Let's keep it like this for now. Let's grab the link and open it in a different tab to see how people will use our game. So as you can see, now you can play this game, and it has a public link, so anyone can play this game on their desktop or mobile. Thank you for watching. If you have any questions, please feel free to reach me out, and have a good day.